Great. So next up, we have Robert, who will be telling us about the properties of negativity and quasi-probabilities and their role in universal quantum computation. Thank you very much.
Yeah, thank you very much. Nice introduction. Yeah, so the title of this talk is Negativity and Quasi-Probability Functions Necessary for Universal Quantum Computation. And I think no, and that is why I'm giving this talk. Oh, okay. Anybody? Anyway, so this is joint work with Michael Zurel, who is a PhD student in my group, Cihan Tokai, and Paulina Feldman. All right, so let me embed this into maybe a larger framework. So the question that we are asking is, what makes quantum computation work? And I think that's a question that fits very well into a workshop on resource theory. As soon as you ask this question, you get lots of suggestions. And I will be focused in the first half of my talk with the negativity and Wigner functions. And I want to illustrate to you that it's a meaningful perspective to say that negativity in Wigner functions is a precondition for quantum speedup. But then I want to ditch it and talk about some other kind of funny feature in Hilbert space, also potentially a resource. But we don't know, we don't have a name for it yet, and we know only very few properties of it. I mean, all these other candidates here, they have long existed before they were applied to quantum computation, and with this thing, it is the other way around. It came up in the context of quantum computation, and now maybe it's an interesting project of study. Okay, so here is the outline for my talk. So I will begin by reviewing a result from the Emerson group that discussed the negativity of Wigner functions in the case of odd Hilbert space dimension. And I mean, this gives you an idea about the whole framework, how Wigner functions come in, which properties of Wigner functions matter, and so on and so forth. Then I will very shortly present a qubit counterpart. And in both of these first works, negativity is a precondition. And then we will change our definition slightly, and we will realize, oh, negativity is not required. So there is a change here going from here to there. And then with this third part, there's lots of open problems, and hopefully I get the time to discuss some of them too. So let me permit to make one sociological remark. So what I'm talking about today is the product of a huge detour. Originally, we wanted to find out something about measurement-based quantum computation, the role of cohomology in it. There was no direct path, so we decided to go on a detour. And there was a point early on in the detour where we learned the essential hint. And we just failed to stop. We just continued on this track, and these two results are what I'm going to talk about today. So this was not planned, all of this. Okay, so let's get started. So let me begin with the review part. So I want to talk about quantum computation with magic states and the role of Wigner functions in it. And this is a review of work of Victor Feitsch and the Emerson group. Okay, so I think this is first slide here is about quantum computation with magic states. It's probably a little bit of carrying call to Newcastle to talk about this at a conference like this. Just the basics. This is a scheme very closely related to the circuit model. It's just we're not using a universal set of gates. We are only using the Clifford gates, which are restricted because of the Gauss-Meinel theorem. Yet, we want to talk about universal quantum computation, and we have to make up for this limitation somehow. And well, we make up for it by bringing in the magic states. It's a particular kind of states, just one qubit states, but outside of the stabilizer formalism. So the computational power must somehow rest within these states. And so we are asking, what is the critical property of these states that makes them useful for quantum computation. And an answer that has been given is the negativity of their Wigner function. So, so this is all in odd Hilbert space dimension. So, so this is how Wigner functions come in. So specifically, there is the following theorem. So quantum computation of magic states can have a speed up only if the Wigner function of the initial state is negative. So that is what Feith and company originally showed, and then there is extensions of it into other scenarios. I will talk about the third scenario here as well, but that requires a little bit of an extension of what you permit in terms of quasi-probability functions. But okay, so this is the structure of theorems that we are concerned with today. So here I say it is a precondition. Later, I want to make a counterpoint, and all of this review is just to prepare for the counterpoint. Okay, Wigner functions. So what are Wigner functions in a nutshell? In classical physics or classical statistical mechanics, you have a probability function over phase space that you can describe your physical systems with. And this probability function can, in particular, be a delta peak. And that is in conflict with the Heisenberg uncertainty relation. So you cannot just import this picture into quantum mechanics. And so you may ask, what is the closest quantum analog? And the closest quantum analog is the Wigner function. But you can't have the exact same picture, and so something has to give. And what has to give is positivity. So the Wigner function can take negative values. That is the difference. So it's a quasi-probability function. Okay. So Wigner's original Wigner function is an infinite dimensional Hilbert space. It's defined over position and momentum. Quantum computation is in finite dimensional Hilbert space. So there is some work of translation required. And that work of translation is easy when the Hilbert space dimension is odd, and it gets tricky only if the Hilbert space dimension is even. Okay, good. So let me talk about these Hilbert space, these Wigner functions in odd Hilbert space dimension. So the Wigner function is due to David Gross, and I will not define it. I will talk about the essential properties. So there's two properties of these Wigner functions that we care about. This is first, their covariance under Clifford unitaries, and second, it is the preservation of positivity under Pauli measurement. So for our picture, these are the relevant properties. So let me quickly introduce them to you. So Wigner function covariance. So I have this written here as a formula, and then there's a picture. So let's go through the formula. So W is our Wigner function, and it lives on a phase space, and it is defined with respect to a certain quantum state. So we have two arguments here. We have the point in phase space, and we have the quantum state that refers to. So on the left-hand side, we have, on the right-hand side, we have some quantum state. On the left-hand side, we have the same quantum state, but transformed under a Clifford unitary. Okay. And so these two Wigner functions are being related. And then the other argument is the phase space point. So here, this is just any point in phase space. Over here, we have a transformed point in phase space. So this is just an affine transformation on the point in phase space we have over here. So what we see from this equation is that as long as the unitary is a Clifford operation, it can be taken on the point in phase space. So graphically, it looks like this. Yeah? So this is a special instance of a Wigner function. It's just a delta peak. And if the Wigner function is covariant, then applying a Clifford unitary, all it does, it moves the peak to another location. Yeah, and the shape of the Wigner function stays exactly the same. So this is the property of covariance. So the other property that we need is the preservation of positivity on the Pauli measurement. So, and what we have in odd Hilbert space dimension for Gross's Wigner function is that if we have a positive Wigner function for some state and apply some projector that measures a Pauli observable with a certain outcome, then the resulting Wigner function is also positive. In the picture, it looks like this. So again, for simplicity, we start with the delta peak, measure it, and then the resulting Wigner function remains positive. Specifically, it has support only on the line in phase space. Good. And so these two properties we now use to derive the result that Wigner function negativity is required for speedup. So what will be proven is the contrapositive. So we say if there is no negativity to begin with, then I have an efficient classical simulation, hence no speedup. And yeah, so the existence of the efficiency of simulation is given by explicit construction of the simulation algorithm, which is of repeated sampling. So a positive Wigner function to begin with is a probability function, so it can be sampled from. Okay, there's fine print here, but in this case, it can be sampled from. And so then the algorithm, once we have that, consists of Clifford gates only and Pauli measurements. Yeah, so the Clifford gates can easily be simulated by the covariance property, and then the measurements are also efficiently simulated because we're just we know that if we start at a certain point, what comes out of the measurement is just stays on the ridge. So I can simulate that by a coin flip. Good. Okay, so this concludes my review of the result of the Emerson group. So this is why negativity of Wigner functions is a precondition for quantum speedup. So goes the argument. Okay, so let me now very briefly, before I go into the core part of my talk, very briefly talk about the qubit case. So it turns out, okay, so let me just repeat what is so weird about the qubit case. So when you take the original Wigner functions and translate them to finite dimensional scenarios, so a priori you might think, oh well, infinite and finite dimension totally different. It's actually not the case. So the transition from infinite to finite and odd is relatively straightforward. But then going from odd to even, this is the tricky part. And I mean, at least from our perspective. And so what fails for even dimensions is Clifford covariance and the positive representation of all Pauli measurements. Yeah, so that's exactly the two properties that we needed for our purposes. And yeah, so they are difficult to get in even dimension. Nonetheless, we can get exactly the same result that we had if we pay a certain price. So this is the theorem that we had before, that quantum computative magic states can have a quantum speedup only if a certain quasi-probability function, W tilde this time, is negative, of the initial state is negative. Okay, but this W tilde is a different construct this time. It's not the same we had before. There is no Gross's Wigner function in even dimension. And the object that we deal with here, that we introduce here, is not unique given any particular state quantum state rho. So given a quantum state, you can represent it by various such the quasi-probability functions. So another way to say this is the phase space gets larger than what you would naively expect. And also gets more complicated and fractured. So this is what changes. If you are willing to admit this change, then you can resurrect the earlier results for qubits. Okay, so let me quickly talk about what happens to phase space. So this is the multi-qubit scenario over here. So you think, I mean, you have one component of phase space. It's just a grid of dimension d to the n by d to the n. You have n systems of local dimension d. And now what happens for multiple qubits, that the phase space splits into various components that you cannot travel by translation. So this, the original phase space, you can travel by translation. Here, you are separated into multiple components. Okay, so it's a much more complicated structure. But if you're willing to deal with that, you can resurrect Feitsch's original result. Okay. So I think I come now to, so the question is where to go from here. So the key point that in doing the same that could be done for the odd dimensional case, we were admitting quasi-probability functions that were not unique. And so the question, is this a legit thing to do? So you can say, oh, well, the quasi-probability function is just a tool, so we are free to use whatever suits us. The con is that orthodoxy doesn't want it. Yeah, so this Platonovich-Weyl criteria require uniqueness for your quasi-probability function. So if you require uniqueness, then you get it into an area of no-go theorems. I do not want to go there today. I would love to, but there's no time. And if you permit non-uniqueness, then something else happens. If you can permit non-uniqueness of the quasi-probability function, then it turns out you don't need negativity anymore. And this is what I want to tell you about. So this is really the core part of this presentation. Okay, so no negativity is needed. We have a hidden variable model for universal quantum computation on magic states. Okay, so let's get started. So, so this was our theorem that we had all along. You need negativity in the quasi-probability function of the initial magic state if you want to speed up. Okay, and so now I'd like to make a counterpoint and to say that this statement really hinges on precisely the quasi-probability function that you use. It is not universally true for quasi-probability functions. And now I want to present you a quasi-probability function for which it does not hold. So no, you can represent universal quantum computation with magic states without ever needing any negativity. Okay, so here's a summary of the result. So we construct a model, a hidden variable model, that has a positive representation of all quantum states, all Clifford unitaries, and all Pauli measurements. So this is not all operations, but it's all the operations you need for universal quantum computation. There's no negativity anywhere in it. Good. And so what is this result good for? So there is two aspects of it. So there's foundations of quantum mechanics, and there is the classical simulation of quantum computation. So so the first thing is we constructed a variable model for quantum mechanics. So in this on this street, we have a bunch of neighbors. We have Bell's theorem, we have the PBR theorem, we have Gleason's theorem, Ferri's theorem, and we must show that we're not in contradiction with any of these established theorems. So I think it is, I mean, independent of doing these consistency checks. I mean, I think it's an interesting observation. The question. So basically it is a random walk model. It's completely classical, but it covers all quantum mechanics and finite dimensional Hilbert spaces. So that's that, and then there is the aspect of classical simulation of quantum computation. So it is a sampling algorithm that can simulate all of quantum mechanics in finite dimensional Hilbert spaces. So where does it get inefficient? So it must have somehow have to do with the hardness of sampling from the probability distributions involved. But we don't know this very well. So the question for us is, where does the efficiency of the simulation end? And we don't know. It's really quite open. There's a few things that we can say. So what we can say is that the stabilizer formula is contained and strictly contained. So there's more efficiently simulable than the stabilizer formulas. Good. Okay, so now let me get a little bit into the details. So what you see here is the definition of the state space that we are dealing with. And so let me just say what got us there after a while was this question. So also the question wasn't clear from the beginning, but after a while we realized the question that we have to ask is, what is the largest state space that is preserved, that is closed under Pauli measurement? So when I have a state in that space, I'm performing a Pauli measurement. I want to move back, not space. I have a set here of states, and I want to perform a Pauli measurement. I want to map back into the set. What is the largest such set? Okay, so this is the question we were led to ask, and this is what came out of it. So this is the definition of the states we're dealing with, and it's fairly similar to a definition of density matrices with one minor twist. Okay, so the parser definition, there is one notion that I need to introduce, and that is the set Sn here, and that's the set of stabilizer states for n qubits. Okay, so with this being said, now the states of our interest are the following. So, I mean, they are operators in Hilbert space of the appropriate dimension, and they are Hermitian and they have trace 1. So, like density matrices. And now, the final property, the trace over the operators sandwiched with the projector onto the stabilizer states. Any stabilizer state is non-negative. Okay, for all stabilizer states. So for density matrices, you would have that too, but you would not have it only for the stabilizer states. You would have it for all states. You would have it for all states. And yeah, so that's the difference. So we are less restrictive than how you would define quantum density matrices normally, and that is related to the fact that we are not allowing all measurements, but only Pauli measurements in our scheme. Okay. So we are less restrictive, so our state space is going to be bigger than the space of the density matrices, or the set of the density matrices. Density matrices will be strictly included. Okay. The final thing to say here is, I didn't show this, but this set of states is a polytope, and as such, it can be expressed in terms of extremal vertices. And these extremal vertices, they have labels, and these labels form our points of phase space. So this is what we consider our generalized phase space. Yeah, okay, and so then the main statement here is that everything is positively represented. So the states are positively represented. That means I can, every density matrix or every element in our set of states is a probabilistic mixture of the extremal points, the vertices. Also, when we take an extremal vertex and perform a Pauli measurement on it, it will be a linear combination probabilistic mixture of vertices. Likewise, the Born world is represented in such a fashion that, yeah, so if we have a certain quantum state and we perform a Pauli measurement, this is represented by a probability distribution representing the state and a conditional probability distribution representing the measurement. And finally, we have Clifford covariance. Good. Okay, and so then our main result is that universal quantum computation by Clifford unitaries and Pauli measurement on magic states can be described by repeated sampling from probability distributions. And so this is about universal quantum computation, and therefore contains all quantum mechanics and finite dimensional Hilbert spaces. So the point is, both the states and the operations are positively represented. All right, so let me relate this to prior work. So first, the prior results are not invalidated. So it's really a matter of which quasi-probability function you choose. So for suitably defined Wigner functions on the qubit, rebit, or qubit case, negativity remains a precondition for speedups. It's a matter of definition, and you can make your definitions differently, and then you get by without any negativity. I want to do one of these consistency checks, namely the theorem by Ferri. Okay, so it says that it is not possible to simultaneously represent all quantum states and all effects, all measurements in terms of positive operators. Okay, so the way we are getting around that is that we don't need all the measurements. We only need Pauli measurements. And so Ferri's result, I mean, the reason it is important is that it makes a uniform statement. It says, okay, so this fact holds for all the quasi-probability functions you can imagine. And so it does not look as fractured as on the previous slide. But yeah, so we don't need to represent all the measurements. We get by with the Pauli measurements. And that's enough for universality. Good. Okay, so the basic question, and I mentioned it already, that remains for us is, where does efficient simulation end? And yeah, so we do not know that. Okay, so let me, I think, is it correct? I have a few minutes. Let me conclude my talk now with the open questions. So the basic question is, where does efficient simulation end? And we can make this a little bit more technical. So the most important thing about the polytope are its extremal vertices. And so can these vertices be classified? Yeah, we have classified the simplest vertices, but it's a hierarchy, it goes up and up and up. So we only know very little about it. So what are the update rules for these vertices on the Pauli measurement? We also know this only in the simplest cases. And where is quantumness hiding in these structures? So these are our open questions. To conclude, let me tell you a little bit about what we know. And let me abbreviate it and go to the last point pretty much straight away. But let me just say, we understand the simplest of the vertices. These vertices have a connection to Majorana fermions. We don't have a good reason for why this is. This connection to Majorana fermions goes quite far. So there is a paper from Sydney that discussed the kind of extensions of the Jordan-Wigner transformations that was based on line graphs. And we found an application of line graphs in our setting too. It gives us new vertices. Okay, let me just and add one more point here about what we know. So in our simulation method, how much information do you need to keep track of during the simulation? And what you need to keep track of is a location in your phase space. Since there is finitely many such locations, finitely many vertices in your phase space, well, that's a number of bits that you need to keep track of. And so the question is, how long is that bit string? Yeah, is this kind of a lot of information, or is it very little information? So remember, kind of this bit string is what replaces the state vector in the conventional quantum mechanical formulation. So we want to know, how long is this bit string? So the naive expectation is that the bit string is the log of the size of the phase space. But that doesn't turn out to be true here in this case, because it turns out quantum computation magic states always start in the same magic state. And yeah, once this magic state is fixed, it turns out you cannot get, by the Pauli measurements and the Clifford unitaries, you cannot get into all of the phase space anymore. You only ever travel a certain corner. And this corner is rather small. And so what we learned from this is that the bit string is really rather short. So if n is the number of qubits that you're describing, yeah, so it's order n squared. Okay, so this is what we have learned so far. Yeah, and so this brings me to my conclusion. So most important point, these lambda polytopes, our state spaces, they are a fun object to work with, we think, and there is many open questions surrounding them. Yeah, so thank you very much.
Yes. Thank you. That was very interesting and very surprising results, at least for me personally. I see lots of people with questions. So Stafford Bartos in the front.
I'm curious because the set that the polytope that you defined, it doesn't seem to be closed under tensor product. So if you have two copies of something that's like positive, then it can be non-positive.
Yeah.
Do you have like an operational interpretation of that, or like because it's very different from the behavior of like stabilized states or positive Wigner function states. So do you have an explanation for that phenomenon?
I would say sort of. I mean, just to back up here, what does this mean? So, so suppose we have a vertex, a 1-qubit vertex, and another 1-qubit vertex, and we tensor them together and ask ourselves, is this tensor product in the 2-qubit lambda polytope? So it turns out that it is not. Yeah. So kind of the tensor product fails in this sense. And what interpretation do I have of this? So none other than, if we didn't have this property, we would be in conflict with the PBR. Yeah. So locality, maybe I can say locality doesn't play a role here in this model, and that is to be expected because of the Pauli observables and the Clifford unitaries that form kind of the classical backbone of this scheme. So they don't respect locality either. So the classical backbone is not some local scenario here, it is the Clifford world, stabilizer world.
Yeah. Let's yeah.
In prior work of yours, you had this relationship between the negativity of the Wigner function and contextuality, which a lot of people seem to like, and I can understand why. And now in this new work where the Wigner function, or this definition of Wigner function, is always positive, do you still have a relationship with contextuality? And do you still feel like that is the somehow engine behind speed ups, if at all?
Let me see. Okay, so maybe one thing I should start with, the most pronounced connection with Wigner functions and contextuality was made by Mark Howard and company. Yes, this is the Nature paper. So for us, the question was, are we in conflict with something like the Cauchy-Specker theorem? And that is not the case, because in our setting, I mean, the Cauchy-Specker theorem it makes, what it rules out is deterministic value assignments for the observables you consider. And the ontic states in our model, they have, excuse me, I hope you could hear me. I was not using this properly, but yeah. So in our model, the value assignments are probabilistic generally. I mean, if you look at an ontic state, maybe a few observables have deterministic values, but typically a number of observables have only probabilistic value assignments. And so we are not in contradiction with the Cauchy-Specker theorem.
Yeah, at the back there. Sorry, the middle one, yeah.
Thanks for great talks. Just for a single question. So you said even in all quantum states can be positively represented under the lambda pointer stacking, but the efficient classical simulation scheme is not known yet, right?
Yeah, and it would be surprising if it exists.
But can we derive the simulation for stabilizer circuit via the lambda pointer technique?
Yes.
Oh, thank you very much.
In the front, yeah.
I was just wondering if there's a version of this that extends the classical simulation of free fermions.
I don't think so. The reason I don't think so, I mean that evolution would be continuous, I suppose. I mean, it would be continuous unitaries, arbitrary close to the identity, and that would require magic states. And that would typically be complicated, it would require a large polytope. So it's an interesting question.
Like, I mean, I can ask
Yeah.
even just a math question. Suppose we take your definition of these Hermitian operators that have to have a positive trace against the stabilizer state. Suppose you replace that with the fermionic absolute state. Is that an interesting set of operators?
Oh, okay, so that goes in another direction. We have not looked at that. I do not know. Here, I really do not know. We have not looked at that before.
Thanks.
We probably have time for one more question, maybe. Yeah.
I was just wondering about when you said Wigner functions, when the Wigner function for a magic state is positive, that statement at the start, is there any possible way to have an operation afterwards that would introduce, on the state, that would introduce negativity into the Wigner function, and then say something about the Wigner function then being negative and then being an indicator at all?
So which part of the talk are you referring to?
Just the claim that Wigner function for particular magic states that are positive or positive Wigner functions. So if you start with the Wigner function that if you start with the Wigner function that for a magic state and that is positive, can you enact an operation later on to introduce negativity into the Wigner function, and then have that mean anything?
No, I mean, not the way the scheme is constructed. So the scheme that all of this works in all three parts is that the operations that are permitted on the initial magic states are either Pauli measurements or Clifford unitaries. And yeah, so that's a computational scheme, and these operations never, in all three parts of the talk,
That's right.
never introduce negativity.
Yeah.
Right, I think in the interest of time, we have to stop there, though I have burning questions myself. Thank you so much. It's a very exciting talk. Thank you. Great ideas.